Assalamualaikum students. In this lecture, we will talk about the radioactive decay law and half-life of the radioactive material. So, radioactive activity follows some law which is called the radioactive decay law. Let we have N naught be number of atoms of radioactive elements at t is equal to 0 time. Let n is the total is the number of atoms at any time t. dn is the number of atoms decaying in time dt. Then the rate of decay, the dn over dt, is directly proportional to n, the number of atoms initially at time. So the minus sign is included, and the minus sign describes that the number of atoms are parent atoms are becoming less with time. With the removal of the proportionality constant, we have a equality, and we have a lambda, which is the decay constant, and it depends upon the radioactive element. From this above relation, we can separate the n terms and the dt terms, and we can have dn over dt, dn over n is equal to minus lambda dt. We can integrate both sides. At time t0 we have n naught number of nuclei, and at time t we have n nuclei, and after the integration we have natural log of n, and the limits are from n naught to n, and on the right hand side minus lambda t from 0 to t. So after some mathematical calculations, we end up, after taking anti-log and so on, we end up with equation number 1, and this equation number 1 is actually the radioactive decay law, which explains that the n is decreasing with time according to this expression. It is exponentially decaying with time, and here in the figure we have n is replaced by a, which is also called activity of the sample. So sometimes it's much more easier to find the number of decays instead of counting the pair nuclei. That the same relation holds with a, which is a is equal to a naught into power minus lambda t, where a is the activity of the material, which usually counts the number of decays. So this radioactive decay law is like this. So from this relation, we can say that after some times the radioactive element is converted into parent daughter nucleus with time exponentially, and we have time, the time after which the half of the atoms, parent atoms, are transformed into daughter atoms, is usually called its half-life or first half-life. So the half-life of the radioactive element may vary from fraction of seconds to million of years. So in the figure you can see the first half-life is represented in the second this second box, in which you have less number of red atoms, which shows the pair nuclei, and the gray atoms are the daughter nuclei. And you can see in the second arrow, which is the second half-life of the material, so you have a less number of pair nuclei and more number of daughter nuclei. So the material usually transformed into daughter nucleus after some number of half-lives. So here's the example of some half-lives. of some elements like lithium 8. It has very short half-life, 0.838 seconds. Krypton 89 has half-life 3.16 minutes, and you can see uranium U-235 has half-life of 703 million years. So it varies from fraction of seconds to millions of years. So the radioactive decay obeys the following two statistical laws. The number of atoms that decays at any instant is proportional to the number of atoms present at that time. This we used during the formation of the decay law. No sample of radioactive element can ever completely decay in a finite time, according to radioactive decay law. So it needs infinite time to decay into the total decay into the parent nuclei. So if we want to find the half-life, so from the equation 1 we have to replace the number of nuclei to n naught over half, because the number of parent nuclei is converted into half number of daughter nuclei at time t is equal to t half. T half is our half-life. So after substitution, the n naught will be cancelled out, and after taking the log, we have the final relation, which is the t half is equal to natural log 2 over lambda, which is the relation valid for the half-life of radioactive substance. So it means we must know about the lambda to find out the half-life of the radioactive element. There is another time which is usually called the mean life or the average life of the radioactive substance. The average life or the mean life of the substance is defined as the ratio of the total lifetime of the radioactive substance to its total number of atoms. It can be found out by the mathematical expression T static is equal to some integration as according to the definition divided by total number of atoms. So we know that according to decay law, in the start of the process we use this relation, and using above relation and some mathematical tool, we end up at the end with the average life or mean life of the substance, which is T static is equal to 1 over lambda. So it is a little bit different from the half-life of the substance. So what is the relation between the half-life and the mean life? And you can see we can correlate them, and T half is equal to 0.69 times T static, because T static is equal to 1 over lambda, and from this relation T static over what mean lifetime over half-life is equal to 1 over 0.693, which means that the mean lifetime is greater than the half-life of the substance. Thank you, students. It is enough for today.